Hello and welcome to Organic Chemistry Companion. In this video, we'll be going over acids and bases in organic chemistry. Now, acids and bases are a super important concept because many of the reactions that you'll learn about in organic chemistry involve reactions between acids and bases. And in this video, I'll explain how to think about them and how to use acids and bases in organic chemistry mechanisms. Okay, so there are two different types of acids and bases. So the first type are called Bronsted-Lowry acids and bases. So a Bronsted-Lowry acid is a proton donor, and that will donate a proton or a hydrogen atom nucleus to a Bronsted-Lowry base, which is a proton acceptor. Now, these are the most common kinds of acids and bases that you'll encounter in introductory organic chemistry, and so for the rest of the video, we're going to focus on these. However, there is another class of acids and bases that are categorized by their ability to donate or accept an electron pair. So these are called Lewis acids and bases. I may make another video going over these, but these are typically not encountered quite as much in introductory organic chemistry. So when we're thinking about the reaction between a Bronsted-Lowry acid and base, we always want to look for the proton that's being transferred. So in this case, I've just drawn a generic representation of an acid, and I have that acidic proton there highlighted in blue. I've also got a base right here, just a generic base represented as B. And when you're drawing a mechanism for this, you always want to start with the electrons on the base. So the base will be attacking the hydrogen atom that gets transferred in an acid-base reaction. So let's just pretend we have a lone pair of electrons on our base, and that's going to attack the hydrogen atom on the acid. And that's going to cause this bond between the acid and that acidic hydrogen to break. Those electrons are going to go back to the acid. So the product of this reaction will be what we call a conjugate base. So the acid now has a negative charge, and the base has picked up that hydrogen, so it now has a positive charge. Now you might be wondering why we use the word deprotonate or proton transfer when we have a hydrogen atom here. And that's because if you notice, so the nucleus of the hydrogen atom is one single proton, there's no neutrons, and the hydrogen atom nucleus is sharing these electrons with the acid. But when the base attacks that acidic proton, those electrons go back to the acid, and the only part of this hydrogen that's transferred is the nucleus, which is just a proton. So that's why we call it proton transfer or deprotonation. Now, depending on the strength of the conjugate base, you can imagine that this reaction essentially could go backwards. So the conjugate base could attack that acidic proton on the conjugate acid, feeding these electrons back to the base. And this reaction essentially would go in the opposite direction. Now the way we draw that is with equilibrium arrows. So to represent that, we have a single-headed arrow going to the right and a single-headed arrow going to the left. And we'll talk about how to think about which direction is favored here, and that has to do with, again, the strength of the acid relative to the strength of conjugate acid. So how do we know which direction is favored, or if an acid-base reaction will occur at all? To do that, we use something called Ka and pKa to tell, and I'll show you briefly where those come from. So if we think about the reaction between an acid and water, we can use something called the acidity constant, or Ka, to describe how readily this reaction occurs. So Ka can be represented by the product of the hydronium ion concentration times the concentration of the conjugate base, divided by the concentration of the acid. And if you think about how this equation works, as the acid is stronger and stronger, it's going to want to dissociate that proton very rapidly and build up a large concentration of the conjugate base and hydronium. And so if the concentration of these species on the right hand of the equation is very high, Ka will be very high, and that favors the forward reaction in the case of a strong acid. Now in the case of a weak acid, you can imagine that this proton will not readily dissociate from the acid, and so the concentration of Ha will be higher than the concentration of the conjugate base and the hydronium ion, so the equilibrium will lie towards the left. Ka will be a very small number, and that's what you would expect for a weak acid. Now, because acids can have very different Kas over a large range and spanning several orders of magnitude, we use pKa as a more convenient way to represent how strong an acid is. And pKa can be represented as the negative log of Ka. So pKa's typically range from about -7 to 50 or so, although some superacids can have pKa's as low as -25. pKa is one of the most important concepts when we're thinking about acids and bases, and it's really important to memorize the pKa's of common functional groups so that you know if they will react in an acid-base reaction. So what is the typical pKa that you might encounter in organic chemistry? So a pKa below 0 is typically seen with strong acids such as HCl or HBr. Between 0 and 5, these are standard organic acids like acetic acid and derivatives of acetic acid. Between 5 and 15, these are weak OH, NH, and SH acids. pKa's between 15 and 30 are most carbon acids, and then pKa's above 35 are for things like alkanes and alkenes that are basically inert under most conditions. So several factors can influence how high or low a pKa is. One of those factors is hybridization. So if you take a look at some of these carbon acids, you'll notice that for methane, the pKa of these protons right here is 60, which reflects that these protons are basically inert to most bases. The protons on ethylene right here have pKa's of 44, reflecting the fact that they are bound to sp2 carbons. And for acetylene, the pKa's of these protons is 25. That reflects the fact that they are bound to sp carbons. Now, another factor that can influence the pKa of a proton is resonance. Now, this proton next to a ketone has a pKa of about 19. And the reason for that is because when that proton is deprotonated, this molecule can take these electrons and donate them into the CO double bond to form this resonance structure. And so the fact that this has a resonance structure makes this proton initially much more acidic. And the same is true for this proton that's in the middle of a 1,3-diketone. So if this molecule is deprotonated, that will result in an anion that can donate into either carbonyl, forming two different resonance structures. And so that's why this molecule has a pKa much lower than any of the other carbon acids. Now, the type of atom that the acidic hydrogen is bound to can also influence the pKa. The pKa of a proton bound to nitrogen in an amine like this is 36, whereas the proton bound to oxygen in an alcohol has a pKa of only 16. And as we saw with the carbon acids, resonance can also make a proton more acidic. Phenol has a pKa of 10, and you'll notice that if you deprotonate phenol, you will form the phenolate anion, which has several resonance structures that you can draw to explain why it is more acidic. Hydrogen chloride is one of the most acidic acids with a pKa of -7. And finally, inductive effects can also play a role in affecting the pKa of a proton. So acetic acid has a pKa of 4.2, whereas trifluoroacetic acid has a pKa of only 0.5. And this is because when trifluoroacetic acid is deprotonated, the resulting negative charge of the anion can be delocalized across the molecule as these fluorines contribute electronegativity to stabilize the molecule. So in general, the best way to master acid and base chemistry is to just memorize the pKa's of common functional groups. When I was taking organic chemistry, I had flashcards, and these worked very well. Once you've memorized pKa's, that'll really help you identify when an acid-base reaction will occur in a chemical reaction, and it'll help you be more confident when you're drawing mechanisms. So if you found this video helpful, please give it a like. That really helps my channel reach as many people as possible. Subscribe if you'd like to see some more helpful chemistry tutorials, and comment below if there are concepts or practice problems that you'd like to see me cover. I also do one-on-one and group tutoring, so send me an email at organicchemistrycompanion@gmail.com if you'd like to get in touch. Thanks for watching.